Okay, the next entry that I would like to add to this table is just the Euler-Lagrange equations. So remember, for a single particle, we derived this. It says dl dq is equal to d by dt of dl dq dot. Okay. Now we want to write down the Euler-Lagrange equation for n particles. Now, let me just pause to make a comment. You know, we keep writing down something for one particle, and then we go to n particles, and I claim that's quite a trivial step. So why is that? Well, so think about Newton's laws. You know, what do Newton's laws say? They say that the force acting on a particle is equal to the mass of that particle times its acceleration. And you don't apply that law if there's only one particle. You know, Newton doesn't say F is equal to ma unless there's more than one particle, and then the law changes. Now, if you have 10 particles in your system, for each particle in the system, you take the force that acts on that particular particle, and that will be equal to the mass of that particle times the acceleration of that particle. So to go from one particle to many particles is rather easy. You just apply the rule for each particle in turn. Using that logic, the Euler-Lagrange equations for a collection of particles, this is well worth thinking through, is equal to dl dqa is equal to d by dt of dl dq dot a. And for a field, we are going to derive this Euler-Lagrange equation for the field in a lot of detail, but let me just tell you what it looks like. So it's the derivative of the Lagrangian density, d phi, of x and t. So you may have guessed that from dl dqa, it just becomes the derivative of the Lagrangian density with respect to phi of x comma t. The right-hand side, maybe you would have guessed, maybe you wouldn't have. So there's a d by dx mu, not just a d by dt. And this is, what are you taking the derivative of? dl d phi dx mu. And those mu indices are summed, and that gives you something that's Lorentz invariant, in fact. So I'll often use this slightly simpler notation. So d by dx mu, I'll just indicate as d mu, and this is dl d mu phi. So the second equation is just a change of notation, no big deal. Okay, so now let's just, so we've made this long table of various things, and let's just try to summarize the logic of what we were doing. So we started from a single particle, 1 degree of freedom, if you like, and then I generalized it to n particles, n degrees of freedom. And this index A told us which particle we were talking about. That generalization was straightforward because anything that you do for one particle, you now do for each of the n particles, okay? And then we did a further generalization, and we said, let's generalize this discrete index A, which runs from 1 to n, to a continuous index x. So in field theory, you should think we've got an infinite number of degrees of freedom, and at each x, we've got a different degree of freedom. That's a perfectly good way of thinking about field theory, and that's the structure that I have been trying to stress by making this table. So there's a very direct link between field theory and particle mechanics. Take one particle, generalize it to n particles, and then make a further generalization where this discrete index A is generalized to a continuous index x. Great. So there's a few loose ends that we have to clear up. So the first loose end is, I want to give you some justification for why we claim that the Kronecker delta is generalized into the Dirac delta. So what's the motivation for that? The second thing that I would like to discuss with you is what is this functional derivative? So we need to discuss these functional derivatives in detail. and to understand how they work. And then the final loose end that I would like to tie up with you is, let's derive the Euler-Lagrange equations of motion for the field theory. So this is an instructive exercise, well worth doing. So let's do that together. So those are the loose ends that we want to deal with. So let's start off with the first one. Why does the Kronecker delta generalize to give the Dirac delta? Okay, so let's start off. So on the left-hand side of the page, I'm going to write discrete version of something, and then I will explain what it becomes when we take the continuum limit. So sum over some discrete index A, I think that you are comfortable with the idea that this becomes an integral, okay? You've seen this many times. Don't be fooled, this is still a highly non-trivial replacement. After all, the sum over A is just an instruction to add up some numbers. Sum over A certainly is dimensionless. If you're doing dimensional analysis, you don't assign any dimensions to the sum over A. Whereas in the continuum generalization, when we look at the integral d3x is a little volume. It's got the dimensions of length cubed. So this really was a non-trivial generalization. So now let's take a look at the Kronecker delta. So where do we use the Kronecker delta? Well, if we've got some sum over A, and we've got some object FA, takes a bunch of values depending on the value of A, and we multiply by the Kronecker delta function, let's do the sum. Well, remember, the Kronecker delta is equal to 0 if A is not equal to B, and it's equal to 1 if A is equal to B. So when we do this sum, most of the time when we plug in the different A values, we're going to be getting a 0. And adding naught does nothing. So the only term inside this sum that actually contributes is when A is equal to B. The term with A is equal to B, the delta AB is just a 1, and FA just takes the value of FB. So you can see what the Kronecker delta has done. It's picked out a single term from the sum. So what would be the natural generalization of that? Well, we would have an integral. We would have f of x. Then we want to write something in here. So let me just leave this as a box for now. And we want that something, whatever it is, to pick out a single point of the integral. So we would like to get f of y. I've used y because b is a different index to a. A has generalized to x, b has generalized to y. So the question is, what should we stick inside this box? And I think you all know the answer, so I'm just going to write it in. It's the Dirac delta distribution. And what's the property of the Dirac delta? Well, when we integrate d3x, the Dirac delta picks out a single point that we're integrating over, in exactly the same way that the Kronecker delta picks out a single term from the numbers that we're summing over, from the terms that we're summing over. So it's in that sense that the natural generalization of the Kronecker delta is the Dirac delta. The Kronecker picks out a single term from a sum of terms, and the Dirac delta picks out a single point from the points that we're integrating over. Good. Now we'll turn to the functional derivative.